This video is created to provide some insight into two very different detectors which have been used on the membrane interface probe systems throughout the years. First, the electron capture detector, and now more commonly the halogen-specific detector, have been used with MIP for the detection of halogenated solvents, which are commonly found as environmental contaminants. The electron capture detector, or ECD, utilizes a radioactive beta-emitting nickel-63 source. As the nitrogen carrier gas enters the ECD chamber, electrons are removed from the nitrogen molecule, creating many free electrons. The now free electrons accelerate toward the positively charged anode, creating a current. As the halogenated sample enters the ECD chamber, the analytes absorb the free electrons, reducing the current between the anode and cathode. This change in current is the measured peak response. The ECD is highly sensitive to electronegative molecules such as those containing halogen atoms, fluorine, chlorine, and bromine. Also, the number of halogenated atoms on a molecule as well as the molecular structure will affect the molecule's electronegativity and thus its response. There are positive and negative effects to this, such as the ECD being extremely sensitive to compounds such as carbon tetrachloride and chloroform, which can be helpful in low concentrations. However, as the chlorine atoms are removed from the molecule, the ECD is not as sensitive to them as we see in the dichloro molecules. Also, when large responses occur on the ECD with very high concentrations, the detector reaches its saturation point, and often the detector remains elevated for extended periods of time due to detector charging and quenching effects. The XSD responds specifically to electronegative molecules such as those containing fluorine, chlorine, and bromine. The XSD operates in an oxidative mode. With internal core temperatures of 1100 degrees Celsius, analytes are broken down into their oxidative products and free halogen atoms. In the middle of this heated zone of the detector, there is an activated platinum electrode. When the free halogen atoms absorb to this surface, they yield an increased thermionic emission, which is measured as a current. The XSD utilizes oxygen, or air, within the detector to oxidize the analytes and separate the halogen atoms from their parent molecule. This process makes the XSD independent of the structure of the molecule. The XSD is also flow rate dependent. The faster the carrier gas moves through the detector cell, the less time for the analytes to absorb to the cathodic surface. The response is nearly inversely proportional to the total gas flow rate through the detector cell. Here is a partial list of common contaminants targeted on environmental sites using MIP. A more extensive list is available on our website. The last two columns compare the XSD and ECD. The spread in the displayed detection levels is due to variations in response each specific MIP system may have due to system wear and maintenance levels of the specific equipment. The detection limit of an MIP system is considered as 5 times signal versus baseline noise. The XSD has relatively consistent detection levels to a wide variety of chlorinated contaminants. The ECD's detection limit to the same compounds is quite variable, again due to the number of chlorines on the molecule and the molecular structure. We are now going to compare the XSD and ECD responses to 4 different compounds which contain either a different number of chlorine atoms or molecular structure. These were performed using the same membrane probe and trunk line, although different GCs were used to vary the detectors. We will start with cis-12DCE, which has 2 chlorines on a carbon double bond. Keep an eye on the detector graph scales as we go through these. The concentrations range from 2.5 ppm to 250 ppm on the ECD, while the XSD was tested up to 1,000 parts per million. The first clear response on the ECD does not come until 250 parts per million for cis-12DCE at a 1e⁵ scale. The next compound is chloroform, which has 3 chlorine atoms on a single carbon. The XSD shows slightly higher but similar response magnitudes, while the ECD scale has jumped an order of magnitude to 1e⁶, with the first evident response coming at 2.5 parts per million. The black line at the bottom is that of dichloroethene. Next, we are adding trichloroethylene to the comparison. TCE is another 3 chlorine molecule, however the chlorines are split on a carbon double bond. Once again, the XSD provides a slightly higher but consistent response level for the tested concentrations, while the ECD sees another significant increase in response, with TC reaching its saturation level on the ECD at 250 parts per million, with much longer detector carryover displayed. The last compound we're going to compare is perchloroethylene, or PC, which is a 4-chlorine molecule on a carbon double bond. The XSD displays very similar responses to PC at the same concentrations as the other compounds. The ECD, however, displays a drastically higher response, saturating at 50 ppm with extensive carryover. Here is a graphical display of the peak response height of each chemical on the two detectors. This truly displays how on the ECD the addition of chlorine atoms on the molecule and the structural changes influence the molecular electronegativity and its response. This also shows how it can be very challenging using an ECD without the aid of a PID or XSD in a highly mixed solvent plume. That said, the ECD can be useful if the plume to be mapped is a single compound like PC or TC in lower concentrations with minimal degradation to its daughter products. One last comparison will be between TC and carbon tetrachloride. Carbon tet has 4 chlorines on a single carbon. This was done on a different ECD and trunk line system long before the previous comparison. Here we see carbon tet in pink saturating at 2.5 ppm and TC hitting the saturation point a bit lower than 25, perhaps in the 15 to 20 ppm range. If mapping carbon tet at a very low concentration was of interest, the ECD could be a good option, but if there's more than a few ppm, the ECD will let you know it's there, but provide zero definition as the detector will be saturated from the first sign of carbon tet until the end of the log. Now we are going to review some MIP logs which use 4 detectors, the ECD, XSD, PID, and FID, and see what we may be able to discern about the contaminants present in these logs from the differences in the detector responses and our current understanding of them. Please remember that MIP logs using multiple detectors allow us to differentiate compound families but not speciate into specific analytes and concentrations. For that information, soil or groundwater samples from targeted depths based on the MIP results would need to be taken for lab analysis. In the first couple of logs, we will show the 4 detectors overlaying the electrical conductivity responses. The majority of the response is seen on the detectors is between 10 and 15 feet. The ECD in yellow shows very little response compared to what is seen on the other detectors, and with the PID and XSD matching well, this is mostly probably dichloroethylene along with a small amount of TCE. The big drop in the ECD baseline at the surface is due to a reduction in oxygen in the carrier gas stream as the probe is being driven into the ground. The second log is interesting as the FID and XSD graphs, numbers 3 and 4, have the first detection at around 5 feet, and the ECD and PID do not start responding until about 8 feet. Between 5 and 8 feet, there may be a dichloroethane, which is a single bonded 2-chlorine molecule, and from 8 to 12 feet, we may assume that there may be something along the lines of PC or TC. For the next 3 logs, we will show individual EC and HPT graphs for lithology, along with the 4 detectors. In this log, the first responses are seen only on the PID and FID above 20 feet, which is typical for petroleum hydrocarbons. The main deeper response is seen between 30 and 35 feet on all detectors with a strong ECD response. It's reaching its saturation point. This is probably a double bonded chlorinated such as PCE, since it's also seen on the PID. In this log, initial responses are at approximately 17 feet with the main body of contaminants starting at 24 to the end of the log in a low permeable zone as indicated by the high HPT pressure. The ECD has saturated at 24 feet and offers no definition. The XSD, PID, and FID are all also responding, so we may again be in a PC contaminant body, and we see some slight reduction in response mass on these detectors once the end of the log has been reached at 30 feet. This final log provides some interesting interpretation challenges. The ECD provides a good indication of contaminants present in a high permeable zone between 5 and 25 feet as indicated by the low HVT pressure readings. The XSD also appears to show some response, but at a much lower scale than what is displayed here because of the response below 30 feet. The ECD indicates the presence of contaminants below 30 feet, but provides no valuable definition since it's reached its saturation point. The XSD, PID, and FID have all reached their initial saturation points at 30 feet. The XSD shows a spike with a sluggish decline between 30 and 35 feet, which indicates the need to change the gain, and while it could have been done to get better data, it was not done in this log. The PID gain was adjusted twice, once at 31 feet and then again at 32 feet, with good data only being displayed below 32 feet. The FID in this log provides the best response with the proper gain adjustment completed by 31 feet, displaying a solid response here. When compared to the other detectors, we can see what they missed. This is probably PC or TC, and since the FID baseline is barely noticeable with responses in the e to the 8th power, it is likely a DNAPL response. The FID provides a great indication of the thickness of the plume mass. Most operators do not use an ECD, and investigators must be careful in the interpretation of data from the ECD as it can be misleading. If one is used, it is best used along with the XSD, PID, and FID detectors.